All right. Hi, everyone. All right. It's great to be here. I really want to thank Professor Howe and Professor Serrato for inviting me out. It's wonderful to see them and then to meet all students and colleagues and postdocs and get to enjoy Albuquerque. It's really a beautiful place and really have some fantastic facilities and really great things going on. So I'm going to talk about the electrocatalytic treatment of nitrate in drinking water. It's basically catalysis, but we're going to supply the electrons for catalysis using a current. The two students who did the work that's unpublished that I'll present today are Chen-Chu Yan and Jacob Troutman. And there's other students who contributed, and I'll have their paper cited as I show that. I've had a bunch of collaborators over the years. I just want to recognize some that I'm currently working with. A couple at University of Iowa, Dave Schwartney in environmental engineering and Sued Mubin, who's an electrochemist. And then two chemists from Texas, Simon Humphreys, an inorganic chemist, and then Graham Hunkelman does DFT, density functional theory type work. And so we've been collaborating together. So like I said, I'm talking about nitrate, and we care about it because there's a lot of it. We put it on agricultural fields and it runs off into soil, groundwater, and surface water. And then we have lots of intensive livestock operations where the urea that they produce turns into nitrate when it gets into groundwater and surface water. It's pervasive enough that it's considered the most common groundwater pollutant in the US. Here, if we looked at what the predicted nitrate levels are in groundwaters, you see that there's this big kind of orangey, yellowy area in the Midwest. And what do we do there? We grow corn, right? Corn needs nitrogen. And so that's where a lot of corn is. We also can look at the nitrogen inputs, that's also concentrated in the Midwest. And so we have lots of nitrogen going into these systems and getting into our groundwater and our surface water. So the go-to technology, if you are at a water treatment plant and you want to remove nitrate, is ion exchange. And basically you have some ion exchange resin, and they're little resin beads, and they have these functionalized amine groups, or one type of resin would. And on that surface, you have some counter anion. In this case, I just show chloride. And so the nitrate comes in, it's negatively charged also, and it displaces that chloride, and the resin absorbs it, and you remove it from water. At some point, that resin becomes saturated, and you have to regenerate it. So what you do is you get a really high concentration brine, and that brine has sodium chloride, right? And the chloride comes in, and it kicks off that nitrate. And what you get is a small concentrated volume of salt and nitrate, and you dispose of that oftentimes. And there's different ways we dispose of it. Sometimes we have brine lines into the ocean if we're near the seas. If we're inland, we might evaporate it in a pond, all right? We just get a salt residue left over, or we might discharge it to a surface water or to maybe a wastewater treatment plant. There's a commercial system sold by Calgon Carbon. It's called ICEP. It's basically like a big rotating table. So it has these vessels on it that are filled with the ion exchange resins, and they're undergoing treatment and regeneration so you can continuously treat this. There's a lot of salt required for this when we regenerate these resins. As high as 60 grams of salt per gallon treated. That's a lot of salt. And salt ends up being the #1 cost of these systems. But right now, we're kind of stuck on these systems. You could use RO, but that's even more expensive. And unless you have salt you're trying to remove simultaneously, it's not really a good option. But nitrate has high solubility, low volatility. It's relatively inert to chemical oxidants, and it has a low sorption affinity. So all those things make it difficult, and it's why we use ion exchange. I mentioned the salt's a big deal. It's about 80% of the operation and maintenance costs, and oftentimes dominate the overall costs of these systems. And then typically we discharge this to the environment. And so you have concerns with nutrients going back and also salinization of different waters wherever you're discharging it. So what we've been looking at for quite a while, for me, about 15 years, is catalytic treatment of these nitrate and other oxyanions. And the basic idea behind the catalytic treatment, this is not electrocatalysis. First, I'm going to start with catalysis. Here we have some catalysts. I have palladium and indium here, and I have nitrate. And the nitrate requires both of those metals, or palladium and some promoter metal, indium, copper, or tin. That nitrate goes to nitrite, and hydrogen is the electron donor for that. The next step, nitrite, can go to nitric oxide, and then we can split and either go to dinitrogen through nitrous oxide or ammonia. In this case, these subsequent steps from nitrite only require palladium, and so they're a bit simpler. When we have nitrate, the thought is that the indium is required, or copper or tin, because they're more oxophilic, so they absorb that nitrate more strongly, and they distort the bonds. The hydrogen comes in, it dissociates to atomic hydrogen. That atomic hydrogen spills over and then grabs one of these oxygens on the nitrate to produce water. And so that's the first step. The subsequent steps, you still have H2 coming in, dissociating to H dot, and then that H dot reacts with nitrite, nitric oxide, nitrous oxide, etc. So that's the idea behind this catalytic reaction. And palladium and indium are conserved. They're not used up in that process. There's been a lot of work in batch reactors looking at different catalysts. So typically you have some catalysts here. Here's palladium and indium on an activated carbon. And you put that in some sort of little reactor here, and you stir it, and you bubble in maybe an excess of hydrogen. And you have in there, you spike it with nitrate, or maybe you start with nitrite, and then you take periodic samples maybe to measure, the products. And you can also take samples of the off gas to measure what those products are. And what you might see is nitrate going away. Maybe you see an intermediate of nitrite or nitrous oxide, and then you'll see the products. And the end products here, I have a mix between N2 and ammonia. And depending on how you run that and what catalyst you choose, you might get all N2 or all ammonia. And you can control that. If we use, for example, palladium and indium, we're going to get high activity and we're going to get high selectivity for N2. If we use ruthenium, we're still going to have high activity, good stability, and we're going to get almost all ammonia. And so we've been able to get very good activity, good selectivity, just using catalytic reduction in batch reactors. And that's showing, hey, there's real promise in this technology. But batch reactors can't be used in real water treatment systems for two reasons. One is it's really hard to mix things in a big giant tank and not have dead zones. And so you have big mass transfer limitations just for mixing. The other reason is that the catalyst particles are banging against each other in a batch, and they tend to just turn into a powder after a while, and you lose them from the system. There's just too much catalyst attrition. And so that's moved people to look at then fixed bed type reactors. And so when we did these experiments, we looked at different types of catalysts. We loaded palladium and indium on alumina, on silica gel, on activated carbon. We looked at exotic supports like carbon nanotubes and carbon nanofibers and other things. And we all, in some cases, we got higher activity. We learned more about the mechanisms, but it still wasn't a kind of a practical scale-up system. So we said, well, let's design a trickle bed reactor. And this was work that we had done with Johnson Matthey, a catalyst company, and also with Calgon Carbon. And they had a lot of work designing these types of systems, not for water treatment, but for more petrochemical systems. And so we, with one of their engineers, designed this kind of three-stacked system where we had the catalyst, we had our water coming in with nitrate, we had hydrogen gas, we used CO2 as a buffer, and as they moved through here, they reacted, and then we collected the effluent and analyzed that. The idea we started with was that we could optimize the flow rates of gas and liquid so that If you have, for example, a low or a high liquid flow rate relative to gas, you get fat water films, and so you have more mass transfer distance. But at a high gas to liquid flow rate, we have thin water films, and we minimize that mass transfer distance and get overall good kinetics. And so that was the idea behind it. And so we built this thing. It never looks quite as pretty as the drawing. There it is. We went to Home Depot, bought a bunch of PVC stuff and other things. We varied hydrogen flow rates over a pretty large range. We varied water flow rates, a little narrower range, but still over what we thought would be a full enough range to explore the effects of different regimes of flow within this trickle bed reactor. And we use CO2 again for pH control. The way the experiment worked is we measured what went into the system. And if you look at this top plot, the top line there is the influent nitrate concentration. And then we had different water flow rates. That's the different colors. So green is one liquid flow rate, red is another, blue is another. And then for each liquid flow rate, we varied the hydrogen concentration or the flow rate. And so we got different liquid to water flow rates. And then we measured the effluent nitrate, that's the solid lines, and they jumped around. And from this, we can take the influent and the effluent concentration, and we can estimate, just using either a zeroth or a first order expression, what that overall rate constant of reaction is going to be for that trickle bed reactor. And so what we did, we took those overall rate constants. In this case, we're looking at zeroth order rate constants. We have a trickle bed reactor from our system, and this is different types of experiments that we did. And we have these rate constants, and then we compared them if we took the same catalyst to what we have in batch. And we also compared them to what was already in the literature. And when we compared them to what we did in the literature, we said, oh, we did pretty good. We really improved the activity of these fixed bed reactors compared to what other people have done. But when we compared them to the kind of what we'll call the intrinsic reactivity, if we're stirring this stuff real fast in a little batch reactor with excess hydrogen, we're like, I don't know, a factor of 10 or 20 or so below what those rates are. And so, that's pretty crummy compared to the batch reactors. We lost a lot of activity. And in the economic analysis we did with Calgon carbon, you know, they say, you know, the batch reactor, those kinetics are promising enough that we can move forward. But when we look at it in a more realistic system, it's really not viable. We're not going to get a payoff given the uncertainty and the other costs and things like that. So one thing we decided to do was just try to understand what was going on in our system. So we developed a little model, and basically we account for nitrate flowing through the reactor and reacting as it moves through the liquid phase. It's reacting with hydrogen, and we have hydrogen both in the liquid and the gas phase. It transfers between the gas and the liquid phase back and forth, and so you have a mass transfer rate constant, this Ka, and then the hydrogen reacts in that liquid phase. And so basically we wanted to quantify this mass transfer rate constant so that we could see how it affects the reactivity when we have different reaction rate constants, K1. And so we fit this to the data, and then we extended it to the case for different types of reaction rate constants of the catalyst. Yes? You have the same material in the trickle system and the batch? We did, yeah. The same catalyst particles. The same activating carbon. Yeah, the exact same stuff, yeah. So one thing is just a simple comparison. Here's our trickle bed reactor activity, and here's our zeroth order rate constants from the batch. And basically, if I look at one set of the data that we did, the ratio is about 100 to 18, meaning our batch reaction rate was much higher than what we were getting in the trickle bed reactor. And if I use my model after I fit my data, I could see, well, if I had higher activities for those catalysts in batch or lower activities, what would be the reactivity in the trickle bed reactor now that I account for that mass transfer? And what they showed was that I was never going to get much better reactivity out of that trickle bed reactor, even if I had a much more active catalyst because of those mass transfer limitations. It just plateaued. And so we were at the maximum we could squeeze out of that system. And so that was pretty discouraging. Well, there's a couple of cool papers. That wasn't discouraging. I like that. And some students graduated, and that's good. They got good jobs. But from a kind of a technological advancing point of view, it's like, that's not quite it. So what are we going to do? So what we decided at the time was to try electrocatalytic treatment. And the idea is that when you have conventional catalysts, right, you have to transfer hydrogen across that gas-water interface. And maybe there's water that it has to move through to get to the catalyst surface that also is tied up in that mass transfer rate constant. If I do electrocatalytic, though, I have protons that are all over a solution, and I can then take an electron and reduce the proton to create atomic hydrogen. And now I can use that instead of splitting H2 to make that atomic hydrogen. And so that atomic hydrogen from the proton can then do my reaction with the nitrate in their intermediates. So that's the approach we decided to take. There are some other things we thought about. We thought about using, instead of our trickle bed reactor, using like a hollow fiber membrane, embedding the catalyst on the surface of those. And people have tried that. And it's some varying success. But there's still some mass transfer limitations, I think, when I interpret those papers that hold that up a bit. So I had a new student, Chen Xu, and we decided to build a reactor. At first, we were looking at something commercial, and we couldn't really find anything and didn't understand how they were put together. And so we built something from scratch, and he did a real nice job. And so he had this peak block. It's just a piece of plastic, and he machined inlets and outlets in it, and that diverted the flow over this cathode. And there's a stainless steel plate where we put an activated carbon cloth here. We fix it to it, and they're electrically connected. So we can connect the stainless steel to the potentiostat here, and this fixed on there, and the reaction happens on this activated carbon cloth, which has catalyst. We have a Teflon sheet here, which is just forms a seal. We have a Nafion membrane that exchanges these cations across that with the anode, and the anode is just a stainless steel sheet here. And so this is Teflon, and then we have the anode, which is just a solid stainless steel sheet. And then we have the flow going on the anode side of the compartment. And so that's basically it. And so all the action for the nitrate's happening on the cathode, where we're supplying a current. And so the electrons are coming in and combining with the protons and then reacting with that nitrate or nitrite. So that was how we designed that. And so we put that into a recirculating system. And it looked like this. Here's that reactor. It's about that big. It's not very big, right? And it's got the influent lines for the cathodic side on top and the anodic side on the bottom, and that Nafion membrane's in there. And here's our reservoir. Then they're just sitting in a little thing of water so it stays constant temperature. And what happens is you just get a little bit of reaction when the water flows through here. And so we recirculate it at a high rate. And so over time, the nitrate concentration or nitrite concentration drops, okay? And so, like I mentioned, for our cathode, we used an activated carbon cloth. And we said, well, let's decorate it with what we've been doing in conventional catalysts, this palladium and indium. And so here's the activated carbon cloth, just an XRD. It's got a little bit of signal from it. When we load the palladium, we get to see the spikes. We don't have any peaks for indium. I don't know if the loading was too low in that case. And then you can just look at TM and see how the palladium is distributed on the surface and see that it's got fairly uniform size and is distributed pretty homogeneously. All right. So we did that. Oops, it went, there it goes. And we started with nitrite, and we did that instead of nitrate because nitrite requires a little bit higher potential than nitrate, and we thought it would be easier oxyanion to start with than nitrate. And so we have nitrite in solution, and we get that decay as it's being electrocatalytically reduced. We do this experiment at different potentials. We fix the potential at minus 0.6 volts relative to a silver chloride electrode. And when we do that, we get a certain amount of reduction over time. We fit a first order rate constant to that, and we get an activity or a K value. And that's what it ends up being at that potential. Then we repeat the experiment at minus 0.8 volt, and we measure the decay over time, and we fit it again, and we get a first order rate constant from that. And so we did that at 4 different potentials. Also, what we do is we measure the current efficiency or the Faraday efficiency. And that's basically if we supply 100 electrons to go to the nitrate reduction, maybe only 50 of them go to nitrate reduction, and the other 50, maybe they were lost because they created hydrogen gas, which bubbled out of our system, okay? And so that would be a 50% current efficiency. So in this case, we see that the activity was the highest at the lowest potential. This is negative, so -1 volts relative to that silver chloride electrode, reference electrode. It drops a little bit when you go to minus 0.6, but if you look at the current efficiency, it shoots up, and it's around 50%, which is pretty good current efficiency at this minus 0.6 volts for nitrite. So that was our sweet spot. Another really nice thing about the minus 0.6 volts is that when we went to really negative potentials, we got almost all ammonia. And that's because when you have more hydrogen in the system, it's easier to take the nitrogen intermediates and hydrogenate them to ammonia instead of getting that N-N pairing. But at that minus 0.6 potential, we only got 5% ammonia, so 95% N2. And so that was what we want. In water treatment, we don't want to go having ammonia sticking around in our drinking water. We'd like to take that all to innocuous N2. So minus 0.6 volt looked like our sweet spot. The rates were comparable, maybe a little bit lower than what we'd seen in the literature, but still, I think, relatively high. And we were getting good selectivity for dinitrogen. So I was pretty pumped up. So let's try nitrate. And so we tried, sorry, I had another step in there. We wanted to look at, for this reactor that we designed, if it was limited by mass transfer at all. And so we took that reactor, and from the results, we developed a model. This came from the literature. It's an analytical solution. When you have a parabolic velocity profile over a surface, that surface is reactive. In this case, we have a reactive cathode. And so this just shows you have basically advection and dispersion in the fluid. This just non-dimensionalization. This just shows that we have at x equals 0 at the inlet, a concentration of 1 for the nitrate, a relative concentration. That at the top of the system, when we don't have a reactive plate, it's just a no flux boundary condition. And then here's the most important boundary. At the cathode, we have a reaction where this is just a normalized reaction rate constant. And there's an analytical solution for this that has a couple of funky roots in there that we solved and then got the concentration that we could solve and match our data. We put this into just a little mass balance for our recirculating system, and we fit our data. And what we did with that is we wanted to look at different things, but one of them was how that nitrite removal varies if we change our intrinsic reaction rate constant at the surface of that cathode. And what we find, these are our data points, the circles, and we're in this regime where as long as the catalyst activity is increasing, the amount of nitrite removal increases, and so we're not mass transfer limited. Only up here does it start to plateau. And so where mass transfer becomes a limiting mechanism. And so what our model was able to show is that, hey, we're not mass transfer limited. So it's a kind of a well-designed reactor. So from that, we decided to try nitrate. We have a really good potential, minus 0.6 volts. We get high activity. We get good selectivity for N2. It's stable. It's not kind of decaying over time, that activity. We also are not limited by mass transfer. So let's try nitrate now. So we tried nitrate, and the results weren't near as good. So this is the plot I showed before for nitrite, and then I show a new plot here for nitrate. And I apologize, the axes are switched on the bottom. This goes from 0 to -1. And this goes from basically the opposite direction, from left to right instead of right to left. But what you see is that when we do nitrate, we can't get at -0.6 any activity for nitrate. We get hardly any at -0.1. We have to go all the way to -1.2 to start getting reasonable activity, or a good activity, and then -1.5, it kind of maxes out. And that's okay, but the really disappointing part is the current efficiency. Here we're at maybe 50%, and here if you look at the current efficiency, the blue, we're at like 2% or 3%. And so we're going to a more negative potential before we get activity, and our current efficiency is really low. And what's happening is we're just losing all of those electrons to hydrogen gas evolution. And so we're generating hydrogen gas. And so why is that? And so we did something called chronoamperometry, where we took our reactor and we just step it through these different potentials. And we hold it at each potential for a little time to kind of overcome the mass transfer limitations until the current kind of stabilizes. And we get a profile like this. And basically what we did, if you look first at the case without any nitrite in the system, you get a little dip here from that purple dots, and then it kind of comes down strongly here. And right here, we're looking at when we're generating H dot, all right, when we're just taking the protons and reducing them with an electron. And when you get, let's say, below -0.6, -0.7, we start getting H2 evolution in the system. And so basically what's happening are these absorbed hydrogen are recombining into H2 and it's off-gassing. And so we're losing our current that way. And so when we look at nitrite reduction, there's a slight dip in the profile here, and we're getting that reduction at -0.6. But with nitrate, we're not reducing it until we're at -1, way out here. And that's where we're getting lots of H2. And that's why our current efficiency is so low, because we have that hydrogen evolution reaction. We have basically a higher reduction potential than we do for our nitrate. And so that makes it problematic. So we did a few things. We varied the palladium-indium ratios. We thought, well, maybe if we vary those palladium to indium ratios, we can get a better current efficiency. And there's different things we tried here at different potentials. We got a little bit of improvement, but still, if you look at our current efficiency, we're like at 3%, which is pretty poor. So we're like, what can we do about that? So there was this really cool paper in the literature where a researcher, Brine Goldsmith up at University of Michigan, he works with density functional theory, and he did these simulations where he was looking at, this would be the same thing as -0.6 volts, but it's 0 volts relative to the hydrogen electrode. Our -0.6 is relative to the silver chloride electrode. But he looked at all sorts of different metals, and he looked at their turnover frequency for nitrate reduction. And that's basically a measure of how active it is, or the kinetic rate constant. It's normalized by the surface area, basically, but it's a measure of that activity. And he also related that to the adsorption affinity of nitrogen and oxygen for the surface of that metal. And he found some neat things that predicted that iridium and nickel and copper and maybe some kind of alloy type compounds like palladium ruthenium or palladium rhodium could give very high activity for nitrate at this potential of -0.6 volts for our system. And so they'd be basically above that hydrogen evolution reaction. And so we decided to try that. And we tried all of the individual metals, the copper, the nickel, the iridium, and the ruthenium. And the only one that was promising So the theory doesn't always tell you what reality is, at least in our experimental system. The only one that looked good was copper. And so we explored that a little farther. And what we did was we looked at the activity and the current efficiency just like we did before. And what you can see is we still aren't getting activity at minus 0.6 like the DFT predicted, but we are getting at minus 0.9. That's still not that great if we compared it to nitrate, but our current efficiency is a lot higher here. We're at 30%. And so that looks more promising. Also, if you look at selectivity, it's not as good as we had for the catalytic system. We're still getting some ammonia here, and we're getting intermediate nitrite, which just hasn't reacted yet when we're starting with the nitrate. But we are getting some good N2. So if we can convert that, the rest of that nitrite to N2, we'd be in really good shape. If not, we'd have some mix, and we still need to work on that. So among those pure metals, the copper showed the most promise and the highest activity for nitrate reduction and a relatively good current efficiency, but had moderate selectivity for N2. But one problem that we saw was copper, it kind of changed kind of funky colors while we were using it. And we measured it in our effluent, so it's not as stable. It undergoes kind of oxidative dissolution when you're cycling it back. So that was an issue. So we've developed this electrochemical reactor. We've shown it has good activity, selectivity, stability for nitrite using palladium and indium. We came back for nitrate, saw it had problems with this current efficiency and selectivity. So we looked at different metals and found copper is the most promising. And so we got to the point now where, well, how do we overcome these other obstacles? And so one thing we did was to go back to this chronoamperometry and look at first, well, what is happening with copper and how can we take better advantage of that? And so again, here, if you look at the potential here, when we look at nitrate reduction with the copper, right, it's around minus 0.9, and that's what we got with the copper. This is for copper. But what we've done with copper is we shift that potential for the hydrogen evolution reaction more negative. And that's why we're getting better current efficiency. So can we still take advantage of these properties with copper, but improve its selectivity and improve its durability? And so that has led us on another kind of parallel track where we're looking at alloying copper with other metals to both stabilize it and also to improve selectivity for dinitrogen. And kind of the idea is an alloy is like a random mix of the two metals. Maybe in this case, we have gold and we have palladium that are alloyed together. In our case, we want to do it with copper and other metals. And so you might think a more noble metal would make copper more stable. And you might look at, well, is there a metal that binds nitrogen slightly more stronger relative to oxygen or hydrogen so that we can get better N-N pairing instead of ammonia? And so we've kind of gone down this path. We started work on this earlier for a little bit different purpose. And we've been working with Simon Humphrey's group in chemistry, and they're really good at making these alloys. And so my student's been working in his lab, and we initially worked on a palladium silver alloy, and this was for conventional catalysis. And the idea was, you know, palladium costs like $1,000 an ounce, and silver costs like 30 cents an ounce. And so if you can alloy silver into palladium and still have high activity, well, that would reduce the cost. $20, not 30 cents, but anyway, a lot cheaper. And so the idea then is we're able to alloy this palladium and silver. And so this is a palladium and silver alloy, and you can see how they're interdispersed, the metals. We can show with XRD how the lattice spacing is intermediate for the alloys relative to pure metal and pure silver. We can show that the nanoparticle size is well controlled and it's monodispersed. So we can get really good synthesis of these type of particles. We can also show that they have advantages. You know, if we look at something that's pure palladium here, or maybe only 50% palladium here, and we mix silver in at different ratios, you know, here we find a maximum activity for nitrite reduction that's at a silver content of about 5% and 95% palladium. And we also, working with Graham Hinckelman's group, we're able to show why that happens because you're optimizing that nitrogen binding energy when you make an alloy in that system. And so the idea then is, can we make an alloy of copper? We've started some initial work with this, alloying copper with ruthenium because we found a recipe and it seems to work, but we want to try other metals. And so ruthenium, I don't think is going to provide the selectivity for dinitrogen. It actually selects almost exclusively for ammonia if you go this direction. It does provide more stability to the copper, though. And so that's just kind of an example of some of the stuff we've been working on. I had one more thing that we're also starting to work on, and that's scale up. We have this little reactor. It's this big, right? You can't treat much water with a little reactor that big. And so we're starting to think about how do we scale up this electrocatalytic reactor. And so we need a residence time in the reactor that's long relative to the reaction time of the nitrate. And so you could look at a dimensionless number called the first Kohler number, where you just look at the reaction time divided by the travel time through the system. And so we want that to be greater than 1. And then we can look at also, we want the reaction basically to be, or we want mass transfer to be fast relative to the reaction time in our reactor. So you could look at another Kohler number 2 there and make sure that's less than 1. We want the pressure drop our reactor to be less than 5 bars because otherwise you have to use high pressure stuff. And so there's different correlations for different types of kind of rectangular channels like you have flowing through these systems. And then in our system, we want control of the potential. We don't want to run it with a constant current. We want to run it at a constant potential so we can control that potential and not get that hydrogen evolution reaction. And so I have a student working on trying to design a scaled up reactor right now to try to take that. So those are some of the new things we're working on. So in closing, the story's not over. Maybe I'll be working on it till forever. I don't know. Maybe we'll solve it. I feel like we keep making steps forward, but then finding new challenges. I think anytime you look at it, putting a new technology into water treatment, it's a big challenge. I think what we found is that these catalysts are sufficiently active to provide a clear advantage over ion exchange in a conventional batch system. But when you start trying to look at a system that you could put into a water treatment scenario, that's not the case, and that's because of mass transfer. This electrocatalysis eliminates that hydrogen mass transfer and the handling of an explosive hydrogen gas, and that's a concern at water utilities. We find that the catalyst longevity, selectivity for dinitrogen, and demonstration of the reactor's scalability are the main sticking points that we're working on. This copper provides high activity and good Faradaic efficiency or current efficiency, but the selectivity and the stability are the challenges. And so we're looking at alloying of that copper and seeing if we can overcome some of those obstacles. And maybe there's also another kind of catalyst out there that we should be considering that we haven't. Reactor scalability seems like a surmountable engineering challenge. There's probably things we don't quite see yet that'll be challenging, but it's a kind of a cool problem to work on. So that's kind of what we've been doing. It's a summary of like 15 years and trying to show you the pieces and how it's come together and how there are still these challenges left. There are other approaches people are taking. I mentioned kind of this membrane approach where you embed the catalyst on the membrane. In the couple studies that we've looked at for that, I think they still have mass transfer issues that are limiting their activity. There are kind of rigid catalytic membranes. Brine Chaplin, a guy at University of Illinois Chicago, developed that approach. It's really a neat approach. I think it could be kind of combined with this where you have kind of almost flat porous sheets you're flowing through. And so it's similar, I think, in that regard. I think the system that he looked at had very high activity and I think good current efficiency, but I think he overloaded a bit with palladium. So when you normalize the activity of palladium, it's relatively low. And so I think he's going back to look at that. But that could be another approach that turns out to be, as good or better. We'll see. So anyway, there's a lot of different people working on this problem. So that's all. Thank you very much. Love to have questions. The reference electrode is it's not a stacked system. It's just one cathode and one anode compartment. And so the reference electrode was just stuck in, and I should have shown it. You see the hole at the top of the peak block there? It's basically a commercial reference electrode is threaded through there, and it sits like a millimeter or two away from that cathode. And so it has a very short distance there. It just comes right in from the top. Yeah.
Charles, I have a question from virtual audience.
Oh, yes.
Thank you for the great talk. I have a few questions. One is for the pack bed design, if you were to do a counterflow of hydrogen and other gases, and if you were to actually implement some sort of recycle stream, what's your prognosis as to how far you can push the limitations in mass transfer rate? And and the second question is, I really like the application of fuel cell design, applying that towards the electrocatalysis. But oftentimes these fuel cell designs, the mass transfer is limited by Nafion, membrane, proton transfer rate, sometimes the electrode flooding, when you can't get rid of the byproducts fast enough. What's your, I guess, projection on, probably similar problems I can anticipate that would arise from such reactor design, and how you would potentially overcome these mass transfer limitations to overcome or to scale this up?
Okay. So first, the trickle bed reactor. Yeah. When we fit for the different flow rates, both the liquid and gas, and got kind of in this intrinsic mass transfer rate, we did look at counterflow operation, assuming that the mass transfer rate constant would be the same. The difference then would be the concentrations of the hydrogen relative to the nitrate. And in that case, just from the simulations, we don't really get much better performance in that system. And so it's really limited to around the reactivity that I was showing. And I mean, maybe there's something we missed, but we looked at it a lot of different angles, and we had also Johnson Matthey and Calgon kind of looking at it and trying to think about it. And so I think we kind of maxed that trickle bed reactor out, but again, there could be something we missed. For the fuel cell work, in our tiny little electrocatalytic reactor that we built, the dimensions of the cathodic chamber, it's like 2 millimeters thick, right? So it's very thin. And the same goes for the dimensions of the anodic chamber. And so we don't have the mass transfer limitations, or at least that's not what held up across that Nafion membrane of our overall reaction, or so for our system, or causing shifts in pH, which are, which alter the reaction kinetics or chemistry. When we scale up, I think that could be a different story, and that's one of the issues. In order to get sufficient reaction times, kind of our estimates, with the kind of the intrinsic reactivity happening on the cathodic surface, I estimate that you need something that's about 2 meters by 2 meters by about, let's say, I think it's maybe 10 centimeters thick. All right, so it's a much larger system. And so are you going to get sufficiently rapid mass transfer across that Nafion membrane? I don't know. You have to have turbulent flow in those systems. And so there are these turbulent promoter sheets that people have explored, inserting them into those cavities above that cathodic sheet. so that you get rapid kind of vertical mixing in that small gap or that 10-centimeter gap where where you're flowing through that chamber. And so I think that requires, putting in a turbulent promoter sheet. Maybe, the other option might be to work with a foam, like a rigid foam in there instead of just a flat cathodic 2D sheet. But I've thought about that, but I don't think I've anticipated all the problems that are likely to come up with the mass transfer issues at those larger scales. So it's really a good point. And that's kind of the thoughts that I've had so far. But yeah, if you have any other insights, please let me know.
Thank you. Thank you. Appreciate your
in the back
answers.
Any what?
Any pulse plating, so like a very short on cycle and then a longer off cycle to get this.
You're talking about the trickle bed reactor?
No.
Oh, in this case, we didn't have mass transfer limitations for this very small reactor, so we didn't try that. In the trickle bed reactor, when we varied the liquid to hydrogen flow rates, you have these different flow regimes that people have characterized in trickle bed reactor. You call it like, your pulse flow regime. Then you've got your, I can't remember. There's like 4 names for them. They got great names. But in one case, even though your flow in is steady, because of the capillary forces, you get these pulses of liquid that moves through there. And so we did try different flow regimes. And through all the flow regimes, kind of the best results that we got are what I'm showing for the trickle bed reactor. For this, for the very small reactor, I don't think it's necessary, and I don't think you'd see any real difference, at least an improvement by pulsing it. If on a larger scale, we design this bigger reactor, maybe that would change. I don't know. It would depend on the situation, so I can't answer that. Yeah. Wondering about the scaling it up. Have you looked at like at losses to the system? Yeah, we did. There was work published in a paper. It's kind of where I got this one correlation. There it is. That delta P, that's a head loss basically as you move through the reactor. For a similar type of rectangular channel, for the dimensions that I was interested in, like 2 meters by 2 meters, they had this correlation, 6.9 times Reynolds raised to the 1.39. And I'm not implying that that one would hold for our system, but it's just kind of like a starting point to look at what that pressure drop might be and how you need to vary the thickness of that flow sheet, basically, to ensure that you're below 5 bars. And 5 bars, if you look at like the ASTM design standards, if you're below that, you can use PVC pipe. But if you go above that, then you got to start using, fancy, much more expensive components. And so we've thought about it and have a correlation from the literature, but I think each kind of reactor and each kind of roughness of the cathodic surface is going to give rise to a little bit different pressure drop, and that's something we'd have to parameterize. Yeah.
Advantages or disadvantages to operating small reactors in parallel with one large reactor?
There must be. I don't know where the right trade-off is. This is certainly too small. When I look at the chlor-alkali industry, they use plate reactors quite a bit. Those are maybe they're on this dimension, right? And they'll be in parallel, right? And so I think if I think about just based on industry kind of experience or what you see out there, the scale is probably somewhere from here to, here, and then it has to be in parallel. You can't get enough flow through one cathodic and one anodic chamber for this. So yes, one of the challenges with having parallel reactors is that, they're sharing basically that same kind of big chamber. And in our system, we brought a reference electrode in from the top, right? You can't really do that. You can't bring a reference electrode into the top. It'll only be a reference electrode for one cathodic chamber. You got all these other ones that are down in the system that you don't have a reference electrode for. So how do you control the potential for that whole system? And that's a tricky issue. Most commercial reactors are running in constant current, galvanostatic mode. And that's not how we think we need to run this right now, at least. Maybe that'll change. Oh, maybe that'll change later on. But one thing we've looked at is the thought of putting the reference electrode in the inlet right before you enter the reaction chamber, and then accounting for that resistance in the solution and calibrating it so you can get what the potential difference is by accounting for the potential drop through the solution. But I don't know if that'll work or not. We wrote that in a proposal. We'll see.
Thank you for your presentation. It's very interesting. And I just have very fundamental questions. I saw in your research, you tried many materials for the catalyst.
Yeah.
First, you begin with gallium, then you use copper, and you try to improve the selectivity and duration for the copper material and transfer it to iodine. So I have a question about, based on different material you have used, does it affect the reaction speed itself, regardless about mass transfer of carbons?
Yes, the material will affect the reaction kinetics in some cases. I would say in most cases. And how it affects it, oftentimes, when it would be nice if we could take DFT, density functional theory, kind of this, theoretical framework, and design catalysts from scratch. As you saw, one of the four metals that the DFT predicted will perform well did perform well, or kind of in the range of what the DFT predicted. So it's an uncertain science. There's quite a bit of uncertainty in it. Usually what happens is we do experiments and we make kind of educated guesses or inferences about how it will behave based on maybe its behavior in another system, like did it absorb nitrogen species strongly in this system, or does it absorb oxygen strongly? If I integrate that, maybe I'll get some intermediate behavior. And then we use something like DFT kind of post experiments to interpret what happened. When we have different reactivity for different metals, I can't, a priori predict what that's going to be or understand maybe without looking at or using DFT or maybe another subset of experiments why it was faster. But yeah, they do show different reactivity, and I wish I had more insights into which direction to go for different metals, but it's a tough thing to kind of predict.
Any other questions? I think we're at the end of our hour. If nothing else, let's thank our speakers.
Thanks, y'all.